Sometimes you can't easily measure the enthalpy of a reaction. So in this video, I'm going to show you what you can do when that happens. We will start off by learning how we can manipulate reaction enthalpy equations and then use those to determine enthalpies of unknown reactions. So the first thing we want to do is take a look at this reaction. We have 2 moles of H2 plus a mole of O2 gives us 2 moles of H2O. Now the overall enthalpy of that reaction is negative 1,144 kilojoules for this equation, for this reaction. Now that is an exothermic reaction. Notice the negative sign on that measurement. So one thing we can do to change this or manipulate or use this, work with this equation, is if we multiply it by a certain factor, let's say we multiply it by 2 or 3, then that delta H of reaction or that enthalpy is also multiplied by the same amount, by that same factor. So we can take this whole equation, and I'm just going to put in parentheses here, and multiply that whole equation by 2. So if I rewrite it, I get 4 moles of H2 in gas form plus 2 moles of O2 in gas form gives us 4 moles of water in gas form. Now if I multiplied every coefficient in that equation by 2, then I also need to multiply the enthalpy by 2. So rather than emitting or releasing 1,144 kilojoules of energy, it releases, if we doubled everything, it releases 2,288 kilojoules of energy for this reaction. So that's one thing we can do to an enthalpy equation. The next thing we can do is we can reverse it if we want. So if we reverse this equation, then we need to also change the sign. So let's just say I want to reverse this equation. I would rewrite it as 2 moles of water in gas form breaks down and gives us 2 moles of hydrogen in gas form and 1 mole of oxygen in gas form. Now if I do this, I also need to reverse the sign on that enthalpy. So rather than it being an exothermic reaction like it was previous, or releasing heat, it's going to be an endothermic reaction. It's going to absorb that same amount of heat. Now the last thing we can do is if a chemical equation can be expressed as a sum of a series of steps, then the delta H of the reaction for the overall equation is the sum of the heats of reaction for each individual step. This is a lot of words, but I'm actually going to show you what this is like, and we're going to use the first 2 rules to actually help us with that third rule. This number 3 here is called Hess's law, which states that the delta H for a series of steps is the sum of the delta H for each individual step. So if we have a difficult time measuring the overall equation here, we can break it up into a series of steps that we can measure. So I'm going to take a look at this first step here. I have carbon on the left and carbon on the left for the individual step. So this step is going to be a part of our overall sum of the reaction. I have carbon on as the reactant for both the unknown reaction, which is in bold here, and then the known reaction. So I'm going to just rewrite that and leave everything as it is. The next thing I'm going to do is I'm going to look at that CO. I have carbon monoxide. I have 2 carbon monoxide as reactants for one of the individual steps, but I have carbon monoxide as a product for my unknown equation in bold. So what I'm going to do here is I'm going to reverse this equation, and I'm going to multiply it by 1/2 to get it from 2 carbon monoxide moles to 1 carbon monoxide mole. Now I'm going to rewrite this so that you can see how that breaks down. I've reversed the equation and I've multiplied the whole entire equation by 1/2. So I get 1 mole of carbon dioxide gives me 1 mole of carbon monoxide and 1/2 mole of oxygen in gas form. Now if I reversed it and I divided by 2 or times by 1/2, I need to reverse the sign and then take 1/2 of that, which is 283 kilojoules. Now I'm going to take a look at this H2. I have 2 moles of H2 as a reactant for this step, this individual step of this known process that I could measure, but I have H2 as a product for my unknown reaction in bold. So what I'm going to do there is I'm going to reverse this reaction and do the same thing that I did previous and multiply it by 1/2. So I've reversed this reaction. So I have H2O as a reactant, and then my H2 becomes a product. So H2O gas breaks down to give us H2 gas plus a half of a mole of O2 molecules. So now what I've done is I've tried to get as many parts of this unknown reaction pieced together as possible. And if I go back, oh, by the way, I need to figure out what the enthalpy would be. The enthalpy would be positive 241.8 kilojoules. I reverse the sign, multiply by 1/2. Now, if I go back, I can take a look at all of these 3 steps and see what can I cancel out. If I have items that are both reactants and products, it allows me to be able to cancel out them on both sides. I have carbon dioxide as both a reactant and a product. And now what I'm going to do is I'm going to rewrite this entire thing with everything that's canceled out eliminated. So what I end up with is carbon as a solid plus H2O gas gives me carbon monoxide as a gas and H2 as a gas. Look at that. That's my original reaction. That's the unknown reaction, the reaction I don't know the enthalpy for. Maybe it was too difficult to measure the enthalpy for that reaction. Maybe I couldn't find the right container or the right environment. So what I do is I take known enthalpies for known reactions and I manipulate them. I work with them. I either reverse them, I multiply them, and then what I can do is when everything kind of lines up and I get this reaction, I can add them all up and get this final reaction, then I add up all the enthalpies of my manipulated reactions and I get the enthalpy of that unknown reaction. This is called Hess's law. So what I want you to do is pause the video here and try to figure out what the enthalpy of this unknown reaction is here. 3 carbons and 4 H2s gives us a C3H8, a propane. Here are the steps with known enthalpies. We have this propane combustion enthalpy. We have a synthesis of carbon dioxide enthalpy, and it looks like a synthesis of water enthalpy. I can use all of these reactions and all of these equations to figure out my unknown. The first thing I'm going to do is I'm going to notice that I have this combustion of propane happening. So I have the combustion of propane. This C3H8 is a reactant in my known equation, but it's a product in my unknown equation. So I'm going to reverse this. I'm going to flip the sign around. So if I reverse the reaction, then the sign, it becomes a positive 2043. So it goes from being an exothermic reaction to an endothermic reaction. So if I rewrite this, I rewrite it with my products as reactants. So CO2 and H2O combine to give me propane, C3H8, and oxygen, 5 oxygen. So I rewrite it. Make sure you include all of the coefficients for the reactions and just rewrite it with the sign, with the arrow flipped in the other direction, or rewrite it so that it's backwards. And remember that you have to change that sign there. The next thing I'm going to do is look at this carbons. I have a carbon reacting with an oxygen to give me a carbon dioxide. But in my unknown equation, the top one, the middle one there, I have 3 carbons. So what I'm going to do is I'm going to multiply this whole known enthalpy equation by 3. So if I rewrite that, I get 3 carbons plus 3 oxygens, 3 O2s, gives me 3 carbon dioxides. And now if I triple this whole equation, I also need to triple the enthalpy that goes with it. So negative 393.5 times 3 gives me negative 1,180.5 kilojoules. So I've tripled that whole equation, including the enthalpy. So that's part of what we can do to work with enthalpy expressions or enthalpy equations. The next thing I want to do is I want to take this 2 H2s, and they're reactants in this, and they're also reactants. H2 is also a reactant in my unknown equation, but I have 4 H2s that I'm dealing with. So I'm going to multiply this whole equation by 2. And if I rewrite that, I get 4 H2s plus 2 O2s, in gas form gives me 4 H2Os in gas form. So I've doubled the entire equation, and I have to double the enthalpy for that equation. So this is an exothermic reaction. It's a negative enthalpy. It's negative 483.6. But if I double that, I get negative 967.2. So what we're doing is we're saying we're going to double the ingredients, which means we're going to get double the products, which means we're going to get double the energy from this equation. That's all we're saying here. That's all we're doing with this. Now, if I add up, I do that step 3 there, the Hess's law, where I add up everything here and just kind of make this into an addition problem. I can cancel out things that are both reactants and products. So I'm going to cancel out the waters, cancel out the carbon dioxides, cancel out the 5 oxygens. I have 3 and 2 on reactant side and 5 on a product side, and reduce this or simplify it. So now I get 3 carbons plus 4 hydrogens, 4 moles of hydrogen, gives me a mole of C3H8 or propane, which is, guess what? This is the problem that I want. This is the equation that I wanted to get to. And then if I can add all of those up and I get the final equation that I want, then what I do is I add up all of my enthalpies. So 2043 minus 1180.5 minus 967.2. Type all this in my calculator. The new delta H for this reaction is negative 104.7 kilojoules. So this is what you do if you can't easily find the enthalpy of a reaction. If you can't measure it using calorimetry, this is one way that you can figure out an unknown reaction. So let's take a look at a more difficult problem. Scientists want to investigate the following overall reaction process. So we get this nitrogen monoxide plus an oxygen atom gives us nitrogen dioxide. We know that this delta H is negative 233 kilojoules. And we also know 2 steps of the process. What we're asked to find here is what is the unknown step and its correlating or corresponding enthalpy. So what we kind of have here is sort of a chemistry algebra problem. So I am going to set it up like I have previously set up problems, except I know my final answer. I know it's going to be NO gas plus O gas gives me NO2 gas. And I also know that the enthalpy for that reaction is negative 233 kilojoules. So what I'm going to set up here is the steps that I know are part of this. And there's a few different ways you can do this, dealing with canceling things out and multiplying different ways, but I'm just going to set it up this way and know that there are a few different methods to solving this. Well, I know that I have oxygen. It has to be one of my final products, or not oxygen gas, but an oxygen atom. And that's one of my steps, actually. Then I know that I have O2s in there somewhere. So I have 3/2 O2 and an ozone molecule, which is O3. But what I'm going to do here is I want to cancel out my O2s because they're not in this overall equation. So what I'm going to do here is I'm going to multiply this entire equation by 1/3. What that will allow me to do is cancel out that half of an O2 that's in that step right below it. So I have 1/3 ozone mole created when a half of an oxygen molecule reacts. So because I took 1/3 of this overall equation, I'm going to take 1/3 of the enthalpy for that. And that allows me, you can see here, that allows me to cancel out that half of a O2, that half of an O2 there. So my unknown for this is going to be 1/3 O3, because I want to be able to cancel out that 1/3 O3 down in the step below it. This is a tricky problem. So I need to include that in my unknown step. And I also need to include the NO in my unknown step, and that will create NO2. So here's my unknown step. This is my, whatever was missing out of that problem here, I need to include in that step. So like I'm going to show you here, that allows me to cancel out that 1/3 O3 and give me a final overall summation of NO plus O gives me NO2. Now I also know that the reaction here, this is a negative 233 kilojoules is known, and negative 247.5 for that step, and I need to take 1/3 of that previous step that I took a third of. So 1/3 of 213.5 is about 71.2. And now what I need to do is figure out the unknown enthalpy for that missing step that I've kind of assembled or pieced together. So I'm just going to set up an algebra problem to figure out this unknown. So x, and then I'm going to add 71.2 and a negative 247.5. So that gives me a, type that into a calculator here. Negative 176.3 equals negative 233. So if I take both sides and I add 176.3 to both sides, then the negative 176.3 is eliminated from the left, and I get x is equal to, type it into a calculator, figure this out, negative 56.7. So that is my unknown enthalpy, and that's in kilojoules. Everything was in kilojoules. I just didn't have enough room for those units. So negative 56.7. So I've figured out the unknown step in this overall process, kind of by doing a reverse of what we did in the previous examples. So this is Hess's law, and this is what you can do if you ever need to figure out the enthalpy for a reaction that's difficult to measure in a lab. You just take reactions with known enthalpies and modify them so that you can have things cancel out and be ultimately added together to get this final equation with an enthalpy that you can just add.